So, we are continuing on Shor's algorithm. So, here we will do the Shor's algorithm once more in the actual quantum stepwise, and we will explain to you how this can be done stepwise. So, the first step, which is very important, is the preparation of the data. As I mentioned earlier, please remember that although the quantum aspect of the process is being utilized in only one of the many steps of the Shor's algorithm, the moment you are dealing with quantum data, we have no choice but to essentially process the whole thing in a slightly different manner. So, although the quantum principle is only going to be used maybe not all the time, it will still be important to understand how this is done. So, in the first step, which is preparing of the data, we will be loading the input register with an equally weighted superposition of all integers from 0 to q equal q minus 1, which is basically 0 to 255, because we said we are dealing with 256 sets. So, the output register will be loaded with all zeros, because we do not know anything about the output yet. So, the total state of the system at this point will be the output register all zeros and the input register containing every possible value from 0 to 255. The comma that I have just put here denotes the registers are entangled. So, that is actually very important. So, this particular part where we are preparing the data has the quantum part incorporated in it, in recognition of the fact that we are considering this to be in the entangled condition. So, that is the part which is important in this quantum principle. The next part, which is essentially modular arithmetic on this entire quantum system, is to apply the transformation x to the power a mod of n to each member of the input register, sorting the results of each computation in the output register. So, this output register, which was essentially unpopulated or were all equally populated with 0, are now going to have the values which are going to be the numbers which are based on the values that we do. And as you can see here, these are now going to have repeats. So, this is the part which is one kind, and this is the part of the other kind, and this kind of shows up the principle that we have been talking about, periodicity, earlier. Okay. So, once we have gotten to this step, okay, which we are all working with entangled qubits, we need to have the case where we can do a superposition collapse, so that we can understand the result, because until that point of time we make the collapse, we do not have the result. And so, we take a measurement on the output register, and this will collapse the superposition into represent just one of the results of the transformation. And if we call this value C, then this is exactly how it will look like. Our output register will collapse to represent one of the following: 1, 4, 7 or 13, right. Because if you look at it, these are the distinct numbers we are getting. Again, the next time all is just repeating. So, at any point of time, if you look at the solution, you will only get these 4 solutions, that is it. So, for an example sake, let us say that we have collapsed to 1 and see what happens as a result of that. So, now since the two registers are entangled, measuring the output register will have the effect of partially collapsing the input register into an equal superposition of each state between 0 and q minus 1 that yielded the value of the collapsed output register. Now, this is the quantum aspect of this entire problem. Okay. The very fact that my input output registers were entangled, when I measured the output register, it automatically affected what was there, and what happened was it partially collapsed the input register into an equal superposition of each state between 0 and 1, such that the result that we measured, the C of the collapsed output register, was there. So, essentially if we have found the value of 1 as my output register, then so considering the case that we are just saying, then the input register will partially collapse to this. The probabilities of each of these cases, as you can see, would therefore be, probability will be 1 over 64, since our register is now in an equal superposition of 64 values which range from 0 to 250. But if you notice, we already have 0, 4, 8, so on and so forth. There is periodicity sitting in there, but let us see how it works. So, the quantum Fourier transform that we have been alluding to, if we now apply that on the partially collapsed input register, what happens? The Fourier transform has the effect of taking a state A and transforming it to a state by given by this. So, in order for those of you who do not remember, this is what quantum Fourier transform does. Essentially any Fourier transform does, which takes any state, okay, it can be, in this case it is quantum state. So, it is a bracket A, otherwise it is any state get state A, which has been transformed into the other get state, which has this particular exponential functional part as associated with it, and this is just the normalization factor which is attached to this kind of a transformation. So, we get this as our overall solution for all of them. A is the set of all values that 7 to the power a mod 15 yielded 1. In our particular case, A is going to have all these values. So, the final state of the input register after quantum Fourier transform will be of this kind, right, because I already have, as I had mentioned in my last slide, that this is my internal register, okay, because all of these values 0, 4, 8, 12, whatever, with this particular weightage factor can be represented by this. Now, it is in entangled mode with the value that I have just measured, which is 1, which meant that when I apply the quantum Fourier transform, the other part, the partially collapsed the input register would now have this value. So, what will happen is the final state of the input register after the quantum Fourier transform would therefore look like this entire thing, which is as a result of getting 1 as my output register. Okay. When I look at this, what we have essentially done is the quantum Fourier transform will essentially peak the probability amplitudes at integer multiples of q by 4, in our case 256 by 4 or 64. So, what will happen is we will be getting values like 0, 64, 128, 192 and so on and so forth. Clear? So, we no longer have an equal superposition of states as we had started. So, that was the basic thing to understand here, that although we started with the equal superposition, the act of measurement of one of them created the input states to also have changed such that it no longer represents an equal superposition, and the quantum Fourier transform essentially peaks the probability amplitudes in such a way that we can now distinguish them. Okay. And we no longer have an equal superposition of states. The probability amplitudes of the above states are now higher than the other states in our register. Okay. We measure the register and it will collapse with high probability to one of these multiples of 64. Let us call this value p. Okay. With our knowledge now of q and p, there are methods of calculating the period of this function. One method is the continuous fraction expansion of the ratio between q and p. Now, this is again a classical principle, and I can explain that in a minute how this classical principle works out. And since we have now essentially measured both the cases, both q and p, we are in the classical domain. So, we can easily do the rest of the process in a classical way. However, until now whatever we did was quantum mechanical, although we used many principles of classical phenomena. But we have to remember that this quantum Fourier transform was essential to sort of understand the or highlight the differences from the equal superposition states in order to collapse them to the periodic function. So, it was essentially the one which found out the way how things are in a state which can now be used very simply to get to the period of the function. And in this case particularly, it is like a continued fraction expansion, and let us see how that works. Now that we have the period, the factors of n can be determined by taking the greatest common divisor n with respect to x to the power p divided by 2 plus 1 and x to the power p by 2 minus 1. The idea here is that the computation will be done on a classical computer. Now, this part is all classical. That is because anyway we are out of our qubit system, the entanglement, everything else associated with is done. So, for instance, then in this particular case, when we know these numbers, we have the periodicity coming out as 4. So, it will be 7 divided to the power 4 by 2 plus 1, 15, GCD of that is 5, and the other one GCD of 7 to the power 4 divided by 2 minus 1, 15 is 3. So, here we have successfully factored 15. Now, the point is, for a simple trivial problem where we wanted to explain the idea to you, it is how this goes, but if you want to generalize it, this is where we started with, this can be done in a much more effective manner. Okay. Now, let me also look at a few aspects which can be of concern while we are doing this. The few problems to look at is that the quantum Fourier transform comes up short and reveals the wrong period. Okay. How to handle that? This probability is actually dependent on your choice of the q. The larger the q, the higher the probability of finding the correct probability. Okay. So, that is the point which we have to remember, that if you want to choose, so even for factoring a number like 15, we chose q to be as large as 256. If I had chosen say 64 or 8 or something small like that, the probability of finding the right answer would have been much wrong, and the period would have been a difficulty. So, the reason why this happens is that if you really want to find a period of any function, you really want to extend the you really want to see how this one behaves. So, you want enough cycles to go, and so if you are working with a very small number to start with, the finding of the period, the oscillation or whatever you want to do in this would be difficult, more and more difficult. So, it is better to use a larger number to work with this. The period of the series ends up being odd. Now, this is one of the cases where you have to actually just go back and pick a new number to start with, because we start with a new coprime in that particular case, because if the period of the series ends up being odd, then the further on whatever we want to do does not work properly, because as you can see, the final step essentially means that we have to actually compute GCD of the period function divided by 2, and once you have odd numbers, this does not come out to be a proper way of looking at the fractions, and so you can run into trouble. So, it is not a good idea if you have odd numbers to go forward. The other part of the problem is that it may be a situation where you can actually get into a quantum modular exponentiation problem, which can be much slower than the quantum Fourier transform, and we always often want to avoid this modular exponentiation part, which we generally do, and we always stick to the quantum Fourier transform method. Quantum modular exponentiation can be always applied, but it is not going to benefit us. So, we do not want to get into those processes. Now, the other part which I mentioned was the continued fraction algorithm, and here is one of the cases. It is a continued fractions in expression of the form where we can represent a function series by just in terms of the fractional part of the starting point. So, if I have mathematical form which contains a 0 all the way up to a m, if it can be represented in this form, then I can actually look at this and get a continued fraction approach in this form. All of the cases will work if a 0 to a m are all positive integers, and any rational number actually can be represented as a continued fraction. So, generally we say that the a 0 to a m components is a convergent of any of these sets of 0 to say m, where so small m versus large m, whenever we have these two cases, we know that we can find out or we can state that these one of them is a subset or essentially a convergent form of the other in the case that m is less than small m is less than capital M. So, we can have an example here. So, for example, if you have the number 31 by 13, you can write it down in the form of a continued fraction. So, basically 31 by 13 can be written in terms of 2 plus 5 by 13 or 2 plus 1 over 13 by 5, which is then equivalent to this form, and then that can be again brought down to this form. Essentially what I am doing is I am bringing it down to a form where all the terms have similar forms. So, we get 2 is the first term, second term we get is also 2, third time I get is 1, the fourth one I get is also 1, and finally we get the term 2. So, this is how a continued fraction can be represented for a number which has been given. Okay. It takes a little bit of a practice, but once you understand the representation as we have just shown you here in an example, you would be able to do this. That is the idea. Okay. Continued fraction algorithm terminates after a finite number of splits and invert steps for any rational number S over R. So, that is actually a good thing about it. This S over R is unique, okay, and R will be the order of the order finding problem, and that is the advantage of using the continued fraction algorithm, because you can always then find the order of the function. So, for example, for n equal to 15, if we go through now the entire process which we have just now discussed all through several times, let me do this once more from the for all the steps. So, for n equal to 15, we choose the random co-prime integer x is equal to 7. Okay. We get the order r equal to 4 from the function as we have done before, which is x to the power r mod n. Okay. So, the GCD of this function is 3, which is a non-trivial factor of 15, and the GCD of that plus form 15 is another non-trivial factor, and so that is how we have done this. Now, there are several applications of Shor's algorithm. One is the, as we discussed earlier in the very beginning, is the encryption problem. Okay. So, the factoring is very important for encryption, because what happens is that if you have a large enough integer, it will take a long time for any computer to find its primes, and therefore, it is an important approach of doing encryption, which is what is happening here today. Nowadays, that is the principle. It is also very effective in terms of quantum simulations, because in many applications of quantum simulation, we require factorization as a part of the problem, and there are many other cases where the technology aspects come in. We will deal with that later. There are issues related to both technology as well as theory, but we will get into these things later on, where we have just listed a few of them here. Anyway, cryptography is related to your factorization issues and not being able to factorization issues. These are technologies which are used to how to do this problem, and the spin off of the theory lies in complexity theory, DMRG theory, representative ability theory. Not all of these are important for this particular course, it is just mentioned here for completeness. Recent work on Shor's algorithm is something which is of interest. In 2001, for example, a 7-qubit machine was built and programmed to run the Shor's algorithm to successfully factor number 15, but no entanglement was observed. This was because this was done in an NMR machine, and in an NMR machine it is extremely difficult to observe entanglement. Although the process of factorization was possible, it is something which is very difficult to observe there, and so that was one thing. In 2012, this principle was updated better, and a factorization was of 21 was achieved, and in April 2012 the factorization of 143 was also achieved. So, presently the process of Shor's algorithm becoming better and better is in vogue. I am sure there have been more work beyond 2012 which has done a lot on Shor's algorithm. However, many a times it is not just the number which matters, but it is more important to find out how you can do better in terms of understanding, and that is why the first few are mentioned here. The later on it is more important to understand whatever you have missed when you were doing the Shor's algorithm in earlier cases. So, that is one part of the problem that we have finished. Now, the other thing which I wanted to do here was to actually give you a few examples of the applications and building scenarios which I have been doing earlier also in a couple of times. I am not sure how these are going to come by right now. I will just take a minute and get back to you on that. So, after having gone through this entire process of Shor's algorithm completely in many different steps over 2 lectures, I would like to actually do this once more in one go, so that you are able to understand how this entire process goes. So, it is a process of revisit. So, let me actually tell you what we have done as of now. The Shor's algorithm essentially contains of 5 steps, with technically only step 2 requires the use of quantum computer. However, as we have mentioned over and over again, use of qubits makes sure that we are essentially going to always use most of the steps in this process to be in the quantum way, except when we have started measuring. So, that I will now mention, where we go to a point where we have started the measure. So, we need not follow the quantum way anymore. So, the first step is the random integer finding, which is going to be less than n, such that they are co-prime. So, given a number n that we want to factorize, we are going to choose an integer m which is less than the number that we are going to factorize, such that they are going to be co-prime. That is the first step. Now, this can be classical. However, the point here to note is that this part would also mean that we are restricting ourselves on the qubit space that we are going to use for a quantum computing. So, that is why this is something where we want to keep as many qubits as available to us. The next step after setting it up, which is technically a classical one, is to use the quantum computer to determine the known period of the function. So, that is the p, the period of the function, which we showed that it could be done by using quantum Fourier transform in the most effective manner. Initially, we create the entanglement between the in the input states and the output states. The output states essentially contain nothing to start with, but it is entangled to the input register that we have created, and then we can apply quantum Fourier transform to go ahead and find out how they can be distinguished from being equal superposition to a point that we can then follow it on to the next step, where we can find the period. The period finding can be done in a continued fraction manner, which is again a classical step. Once we get there, then everything further on can be done in a classical manner. So, the step 3, which is where the period, if it is integer, does not allow us to go any further, because the next periods, next parts essentially involve mathematics which would not work precisely if we keep using the odd integer. So, we have to go back to step 1 and start the process again. However, if it is an integer, even integer, then we can go to the next step, where we can find out the cases of mods between the +1 and -1 case of the numbers that we have found with the periods, and we can find out the case where if we get trivial solutions, then we go back to the first step. If we do not get the trivial solutions, we can continue on to get the the final solution, which will be the factors of the numbers that we have chosen. So, this is basically the principle. The order finding problem can be classical, but in the case when we are actually using quantum mechanics, we generally also would like to put this under the quantum sense by applying a quantum Fourier transform. However, once we have measured the periods, or once we have measured the factors, once again we do the process of continued fraction to be able to get these problems, and then we can go ahead with the first part. So, the classical part essentially includes 4 steps, except the step 2 which we did. So, in the classical form, the random number is the one which is chosen. Then this part which is again which is doing the Euclidean arithmetic, which does the GCD finding, can all be done by using Euclidean arithmetic. So, in between this random number generation part to the part where we are going to find the orders, we do the critical step of setting up the register and the output register, setting up the entanglement after them, and finding a quantum Fourier transform, so that we could make sure that the members of the incident input bits are different, and we started off from equal superposition here. These different set of numbers are then helping us to find the measure of their numbers, the collapsed measure numbers, and those measure numbers are then utilized in a continued fraction method to find the period. And once the period of the function is found, then that can be again used to find the GCD, and then the factors, and then we can keep on going back and forth by this principle. So, the only path which is quantum mechanical is essentially embedded in this part, which is where the part is explained. You can, for trivial problems, you can actually see how it works in terms of the classical way of finding the periodicity. You find the values of all the possibilities of raising it to the numbers, and then taking their mods and getting those values, and you can see that every fourth number, after every 4 numbers in this particular example of factorizing 15 with the choice of the co-prime as 7, after every 4th number the repeating starts. So, we have a period of 4. Now, this in the quantum way of looking is able to happen, is possible to be made understood when we do the registers, and this is what was being explained here, where we chose the number such that we were able to first pick the particular value of x. Once we picked the value of x, which is the co-prime, then we went into the QC mode, and in this QC mode it was important that the integer that we chose was large enough. Okay. Now, that also we have seen in the pitfalls of the Shor's algorithm case, that this large enough number is important, and so this is something where this part is to be taken care once more. So, once we have understood this idea that the principle of picking the value of the co-prime is the part which is classical, we have to be careful in making sure that we choose the number q which lies between the n squared and 2n squared values. That is the part which is not going to be too small. Then we can use that number to set up our registers, because this number q is something where the periodicity will be finally coming out from, and if the numbers are too small, then our periodicity does not find out to be good. So, that is the reason why these are the periods where we have to be careful. The quantum part was once again explained slightly better here when we use the Fourier transform method to sort of make sure that one of the registers, which is the input register, which was affected as a result of measuring the output register, could be made to be set in a way so that it can be utilized later to find the period. And so, the way it was done was take the idea of measuring the first register, and then to the second register which was left over was then continued to go ahead with the continued fraction approach. So, here is the once more the idea of the preparing of the data which we focused on today, where we loaded the input register with an equally weighted superposition of all the integers from 0 to q minus 1 with the value of q that we had chosen. The number better be a large number, otherwise it will be difficult to get the proper period, and then the total system at that point is then utilized as an entangled set with the input register and the output register. We measure the output register when we apply the transformation x to the power a mod a to each member of the input register. This is the quantum approach, and store the result of each computation in the output register. This output register measure essentially ensures that the input register values dependent on the exact value that is measured at the output register. So, of all the possibilities, so here we go. When we make a measurement of the output register, this will collapse the superposition to just one state. Now, this is the part which is most important, because it is an entangled situation. Once we have focused on one of the measurements that we make, which is just one, then the rest of the result which exists in the input register is now collapsed also to represent only one of the following sets. So, once we say that our output register will collapse to represent one of the following of the possibilities, we have in turn also affected the input register. So, this is the part which was very important, where we removed the equal superposition principle of the input registration case because of the way how things are now. So, when we take a measurement of the output register, this will collapse to a superposition to just one of the result of the transformation, and once we choose that, let us say the value c, in this case it can be any one of them. In this particular example we had to chosen 1, then the input registers also got transformed from their original value. But please note, it would still be in an equal superposition of each state between 0 and q minus 1, which yielded the C state. So, this is the part which is very important still, that the input register still remains in an equal superposition once we have done this collapse measurement of the output case. So, the partially collapsed input register will be of this kind, with each probability coming out as 1 over 64, which means these are all equal superposition. Right. Now, with this we cannot go further, because if we have equal superposition now, we do not have a way of going forward to find periodicity or other things in a quantum register. We have to do something more, and that is the part where we applied quantum Fourier transform. Once we applied the quantum Fourier transform on the partially collapsed input register, the Fourier transform has the effect of taking a state and transform it into a state which has the periodicity sitting in there, which makes the input set no longer equivalent. That is the most important part here. So, in our particular case, what happened was the final state of the input register after the quantum Fourier transform ended up being something like that, which is entangled to our measurement that we saw, which was 1, which meant that it peaks the probability amplitudes at integer multiples of q by 4, which in our particular case is 64, right, and we no longer have equal superposition of states. So, only those states which are represented as 0, 64, 128, 192 and so forth, multiples of 64, which have been seen. The others, which were supposed to have equal superpositions, are no longer available in that sense. So, in this particular way, if we now measure the register, it will collapse to the high probability of one of these multiples of 64, which we can call as some value p. Now, given the value of now p and the q that we started off with, we can then find methods, classical methods, which will help us to find the period of this. Okay. So, this allows us methods of calculating the periods. One method is continuous fraction approach, expansion approach of the ratio between q and p, which is quite popular, and it turns out to be computationally quite good, and that is the classical one which I have shown later on in one of the slides to show it to you as to how that represents the actual result that we are looking for. So, for example, once we have so that actually gives you the period. So, basically once you do this, you would be finding out that that will give rise to the period of 4, and once we get that, we can essentially automatically calculate the two factors. Now, in order to get to that period of 4, so these are the error parts that we looked at, but in order to get to the period of 4, what we did was we basically showed you an example where we essentially showed how the continued fraction principle works. We took any two numbers and we showed that you basically can write it down in terms of this and write it in these forms, and similarly if you do that for the case that we are looking at, for any rational number there is a unique value, and the number, as long as the value which is going to be given by, so what we will be finding is we will be finding S over R, where this R is going to be, S over R will be unique. The R will be the order of the finding process of the problem, and that is what we found, and this is the way we finally showed you that for the number 15 found in random coprime integer and integer x, which was 7, we get the order R for the function, okay, by applying this principle. Once we get that, which is how we showed in terms of continued fraction method and others, we can go and find out the non-trivial factors of 15, and that was the basic idea. So, with this I hope we have understood the principle of Shor's algorithm to a level that it can be utilized and implemented in the quantum way, and this is one of the cases where the actual entanglement process of quantum qubits are being utilized, and so this is the most effective approach and shows exponential advantage over the classical case. In the next few cases lectures, we would go into more and more applications based on all the understanding that we have developed as of now. Thank you.